Hi, my name's Adam, and I got a question for you. Are you ready to talk about multiple controller simulations at a higher level language that compile down to C? Well, I hope so, because about 10 years ago, I wrote a Java to C99. Don't throw your bok choy at me. Um, yeah, Java, it was a good tool at the time. We're basically going to talk about this project as a whole and some of the massive benefits that I got from it, but we're not talking about doing this again. All right, so let's get going. Right, this is part 3 of a video series. We've talked with an intro of Fin, some Fin language features. Up next, we got embedded C software testing and design choices, a language comparison, and then finally wrap up with implementation and challenges of Fin. All right, let's get going. Story time, Java to C. So yeah, I created a Java to C99 transpiler about 10 years ago, and it was cool. I basically wrote C inside of Java, and I got that highly modular code that was testable, and it would generate into highly efficient code with no heap, not a heap, and ran on a PIC24. Yeah, I used this for a commercial product, and through the development of it and all of the testing and simulations that I didn't find a single bug in the field, which was great because we had no way of dealing with that. All right, so a little bit about me. Um, yeah, so why did I pick the PIC24? We'll go over a little bit of background here. I was actually really lucky to start electronics consulting in high school, which is around, I was near the end of high school. It was around year 2002, for two different entrepreneurs. Chris lived in Brandon, which is where I grew up, and he just wandered into our electronics class one time and he was like, "Hey, anyone here want to make some printed circuit boards for money?" And I was like, "That sounds cool." And so I got started with very simple stuff like preamps for microphones and stuff like that. And then very quickly we moved on to microcontrollers. And then also around that time, I met George online because I was also like really keen on paintball. And I met him online and he was interested in creating some cool stuff. And so we started talking. And actually, near the end of graduating high school, uh, so around 2003, I started work with George, and that continued into that was like my employment for post high school before university, was creating a paintball wireless bassmaster system. So different bases, there were like three different bases, a white, yellow, and a red team. And there was a central display, or yeah, basically a central control and display thing here, which had like just a ton of LEDs. It was all wire wrapped and soldered, like all the LEDs were soldered. It was a proof of concept. It worked. It was really cool. Um, Here's an example of it in the field here. But unfortunately, I couldn't convince George to spend another couple $100 going from a wire wrap solution down here into a PCB. So it worked in the field for about 2 weeks, and then I think somebody bumped it in the control center, and one of the wire wrap leads broke, and that was kind of the end of that project. And George, from my understanding too, like I offered to try to like fix it and that kind of thing, and he hadn't really thought through the whole process of like going from paintball field operator into like manufacturer. And he was like, you know what, it was a really cool project. I learned a lot from it, like George did. I learned from it too, and so we just kind of let it die. But it was a really cool project, and it was all written in assembly with the PIC16. If I ever meet you in person, ask me more about George. There's some fun stories there I can tell you. Right. Now, I fell in love with Atmel AVR. I didn't learn C in high school. I was doing more electronics rather than programming. So I did everything in assembly. And when I went for my next project, I decided I needed something other than PIC16. It was cool, but like I didn't want to use PIC Basic anymore. That was great for high school, so I was writing everything in assembly, but the PIC16 assembly was not great. And so I started looking for alternatives, and when I switched to Atmel AVR assembly, I was like, oh. Now, I found this quote a long time ago, and it'll always be in my memory, and I'll share it here. This is from a website. Overall, I've written some assembly for both processors, and I hate to break it to PIC users, but writing assembly for PIC is akin, specifically PIC 16, is akin to stabbing myself in the face. Except it's not even that efficient, because you have to move the knife into the working register first, move knife into the working register, and then stab yourself in the face. Yep. That summed up my experience with PIC 16 quite well. And there's all sorts of like bank issues and other stuff that was annoying. I love that quote. Anyways, this comes from Lady Ada, who I didn't know at the time, but she became the founder, or like is behind Adafruit, which is also really cool. All right, a quick little bit of history on some of my mistakes going from early developer into more commercial products. While I was in university, I was designing an expansion camera product for Chris, and it was like our third or fourth microcontroller product, and we wanted to keep the part cost low. So I selected the AT Tiny 2313, this beautiful little chip here. But I messed up, big time. It was super tight on RAM, and it had like 128 bytes of RAM. I needed 2 communication interfaces, but I was like, you know what? I can bit bang another one. Yep. Any part savings was neglected by the extra effort that I had to take. And I ate pretty much all of that extra effort. I didn't pass it on to Chris because like it was my judgment call. I made a bad one. Anyways, we were selling hundreds, not thousands of products. It didn't make sense to do this. It worked well. It was really interesting. I enjoyed it. But looking back, I'll never make this mistake again. If I need 2 communication interfaces, I'm going to buy a chip that has 2. So be simple here. So yeah, I learned lots there. I took another side job for Chris while I was working for a telco after getting a computer engineering degree. And yeah, the Chris work never did pay great, but I learned a lot. I benefited a lot from the experience. It was really good for me. So I knew for this new product, I know I needed 2 UARTs, and I didn't want to bit bang anything for commercial work ever again. But for fun, I did create an AT Tiny 85. That's like an 8-pin DIP chip that would generate NTSC video character, like a display. It was meant kind of to like replace that failed paintball display that had all those LEDs everywhere. I was like, okay, if I wanted to do something like that again, how would I do it? And so I was just playing around with generating video signals, and I got pretty far actually. It could support 400 characters. We could have different black and white shading for the characters and invert font, borders. It was really cool. I never did fully finish it because I could only get the even fields or the odd scanline fields to work. When I tried to interlace them like regular NTSC video, yeah, somewhere there was a little bit of jitter. Unfortunately, I can't find that code anymore. Makes me sad. I think it's on some old laptop somewhere. Right, so this product was called the MPTZ, and I know I needed 2 UARTs. I was done being dumb and trying to use small AVRs that only had 1 UART. But I looked at the PIC 24, and I was like, well, it's got a free C compiler. It's got 2 UARTs and enough RAM for buffering those UARTs. And it's not a PIC 16, none of that garbage. So yeah, I went that way. So if we take a look at what the product was, yeah, I was contracted to do the hardware and software by Chris, and it's the MPTZ. Stands for multi-pan tilt and zoom. That's mostly, oops, mic bump there, apologies. Yeah, most of what Chris was doing was pan tilt and zoom stuff for farmers. So it's basically a smart wireless connection that would allow a farmer sitting from the comfort of their house, maybe a kilometer, a few kilometers away, to monitor cows and livestock in their barn, especially during calving season. I guess that's pretty important. Farmers will sleep with like a TV on with this camera going, watching a particular cow. And so like when things get interesting, then they wake up and run to the barn and help make sure that the delivery goes well. So they have this pan, tilt, and zoom controller. It just takes RS485. It would go to our MPTZ. and we use an XB radio, 900 megahertz scope, pretty decent range, and basically connect the pan, tilt, and zoom controller to a camera. So in this product here, I wanted to do something fun too. I didn't want to just bang out some more C. So I created this Java to C transpiler. I was learning more about code in university, and I wanted to do something cool. Now, I didn't get Chris to pay for the transpiler. That was all on me, and it was really fun. It was really cool. And it had a huge benefit too. Before the custom printed circuit board was available, I actually had my Java code, which is like the application, all the application logic. It actually interfaced with real dev kits, real PTZ controller, and real PTZ camera with serial ports. And this was pretty easy with Java actually. So the connector would go, or sorry, the controller, the joystick would go RS-485 to a COM port, run in my Java code, acting like the actual MPTZ project. It would go to RS-232. Those radios would actually talk, the dev kits, back into my same laptop, and then out again to the real hardware. So I could test pretty much everything except for like my very low level UART drivers from Java with one computer. And this was extremely powerful. So how did this work? Well, the Java code was flexible enough, because it was written in a high-level language, to use fake UARTs connected to COM ports. So I've got my application code. It sits on top of a UART, or it uses a UART1 driver and a UART2 driver. When I'm simulating on my laptop, I just fake out the UART and connect it, or the hardware equivalent of the UART, and connect it to a COM port. Yeah, but the generated code that came out of the transpiler, it didn't have any of that weird abstractions or anything. It was just the UART1 driver would use the PIC24 UART hardware abstraction layer. And it worked really, really well. So if we just look at the data flow here, I'd get RS-485 in, it'd come up through the COM port, through the fake, into my UART1 driver. The application code would do some stuff with that, send out a new message through UART1, the COM port, RS-232 radio, RS-232, up the fake, down the fake, and back out to the camera. All right, so one thing that this helped me with, and this is actually huge, was that in my simulation setup, instead of using real hardware radios here, I could actually pop in with Java, or my high-level language, a simulated radio PHY here. And this was really cool because I kind of had like my own like Wireshark ability where I could see everything that the house side was sending and receiving, and the barn side, what it was sending and receiving. And then even cooler than that, I had a GUI where I could adjust the bit error rate. So I could really mess around with things and see how my system behaved. Now I had full control over the simulated RF noise. We could have burst noise, whatever randomness or bit error rate. And this was really cool because I could get a real life feel for how my protocol would work in challenging radio environments. So I'm working on a real real joystick over here, and I can see my camera moving over there. I can test the responsiveness, find some issues, and I did find some issues too. One is that when this sends a command here, it basically sends like a move command, and then it sends a stop command. And if the stop command is missed due to radio issues, then this thing would just keep on spinning. And so we played around with different timeouts and found something that worked out well. And there's some other issues that we helped figure out too. And this was just so much better than trying to do this in field testing, where you'd like drive miles apart, use walkie-talkies, where I'd be like, okay, Chris, I'm about to move the joystick. Shout back at me as soon as you see the camera move. Like that just, it's just a bad time. And like, if you're trying to simulate particular RF conditions where like you're on the edge of a connection, like doing this in the lab was just so much easier. I found all the issues and fixed everything from my lab. Now, we actually went more advanced than that last slide showed for the radio PHY. I included asymmetric bit error rates. And this might seem a little bit weird because if you're familiar with radio, we've got, like, if you think about the free space path losses from the barn, or from the house to the barn and the barn to the house, they're symmetric, they're the same. However, noise source locations are not. So maybe in the barn, a farmer would have a 900 megahertz walkie-talkie, so you get some burst noise here, and that'll mess up the receive kind of radio PHY coming into the barn. Or in the house, you might have a 900 megahertz cordless phone, similarly messing up the receive side for the house. And because of the custom protocol that I wrote, and we use something custom because to get max range, we ran at a really slow baud rate. So yeah, the custom protocol included acknowledgements and retries. It was bidirectional. And so it was important to test with like asymmetric conditions where maybe we're sending commands to the barn and the barn is fully receiving them. It's acting on them. Everything's working well, and it's trying to transmit back, and it is, but it's getting lost at the receive side because of noise source over here. So being able to mess around with our protocol and make sure that it behaved in every condition was also really helpful. All right, and one other thing that was really, really powerful about debugging or having this all on my one laptop instead of like out in the field or on multiple controllers is that I could debug it all together. So I have a simulation here running in its own process. It communicates via TCP to the RF PHY simulation and also a simulation monitor, and then connects to the barn simulation. And what the reason of the sim monitor here was that it would detect if I hit a breakpoint on either side in either code, and it would tell whichever side was still running to pause. So if I set a breakpoint in the house code and it hit the breakpoint there, the sim monitor would right away figure that out, or actually get a message from that side, and then tell the barn to pause as well. And what was basically, this was incredibly helpful for debugging multiple controllers together. And then eventually when I resumed control over here, it would resume there. Using it with two, not that big a deal, but if I was doing like a mesh network where I had like 10 different controllers or something, this could be huge, this kind of behavior. And yeah, just to drive this point home, before I added this feature, when I hit a breakpoint over here, this side would stop on the house side, but the barn side would keep on running and it would time out pretty quickly. And so whatever like kind of statefulness that I had established in the communication protocol would quickly be lost on the barn side because it would run and time out and then boom. So it was always a pain in the butt. But being able to synchronize those together was huge. Now, this worked, but was a little bit hacky. If I was to do this all again, I would experiment, and I will do this again someday, probably soonish, in maybe a year or so. I'm going to try to keep it all in a single process instead, because I had to do a little bit of hacking to try to get all of them to stop at the same time. Incredibly useful, though. The other thing that was really, really, really cool was that I could fuzz like one controller against another controller. So instead of having an actual hardware controller over here, I'm generating some pan, tilt, and zoom commands here, like in simulation code. And then on the barn side, I don't care what comes out. So I just say, okay, whatever's coming out, just send it to null. Or just like check it for basic sanity things. It's not connected to a real camera. Anyway, it did help me find a really tricky error. So in hardware, I was testing in hardware one time, and I noticed a weird condition. And I looked at the code, and it was basically like a switch case, where at the end, you have your default, and you're like, well, it should never get to here, but if it does get to here, throw an error or something. So I set a breakpoint in that error, and I couldn't figure out how it was getting to there. So I ran a simulation overnight where the house was talking to the barn, and we had random injected radio errors. And in the morning, it hit that breakpoint, and I was able to look at the stack, all the variables, the message history back and forth. And once I kind of clued into what was happening, it was really easy to fix, but this is not something that I was going to find with regular unit testing. And this is one of those things where I was like, I was super grateful that I found it at my lab instead of in the field, because yeah, we didn't have an ability to do in-field updates. And one other thing that was really handy about this too is that the generated C code had no idea about exceptions at all. They just didn't exist. But during simulation in Java land, or magical high-level language land, I could throw exceptions, kind of like, think of them like assertions, but like with really high fidelity, where you get stack trace and all that kind of good stuff. Yeah, no exceptions in generated C code. Now, the actual Java code don't think of it like Java code. It was really me writing C, but with Java syntax. It was actually doing everything. I didn't write any handwritten C code at all in there. It basically accessed registers and peripherals and assigns them values. Yeah, it was all done in Java with some special annotations to do a couple interesting things, but just to show what's possible for Finn, we could do this as well. So overall, it was a huge success. The result of easy unit testing and simulating in my lab, we didn't find a single bug in the field in years of deployments. No expensive field updates. Just to talk about that too, like even in like my current work, some of the products that we work on, if you have to send out a technician to the field or rely on a dealership to go out to a farmer's field and do an update, it's hundreds of dollars per hour. Like if you have to do this across an entire field, it's a big deal. So the more we can make sure that our code works properly in labs or simulations, way better. But yeah, Chris was happy, the farmers who used it were happy, and I was really happy too. So if I've already done this, Java to C, why aren't we doing it again? Well, the big kicker, and something that really sucks about Java in general, in my opinion, is that it doesn't have proper unsigned integer support. I guess, was it James Gosling, the inventor of C? Or sorry, not the inventor of C, the creator of Java. He seemed to think that programmers weren't smart enough to be able to figure out how to mix signed and unsigned. And actually, C# takes a much more sane approach that you can do when it's modern. We won't talk about that too much here, but yeah, that sucks. I'm an embedded developer. Don't take unsigned away from me. And so in the end, that transpiler worked, but I didn't see a future of using Java. It was a great proof of concept, but I needed something else. Around that time, C# was becoming open source, but it didn't have the features that I thought I could make it work with at the time, but it does now. And so we can do things like C++ style destructors, or RAII. I don't know if there's a shorter way of saying that, but resource acquisition is initialization. Anyways, we can emulate that in C# with using statements. We can also detect memory issues like use after free with full stack traces in C#. And we can also, because of operating overloading in C#, which will not be supported in Finn, we're just going to use it for our simulation zone, we can implement our own custom numeric types that we talked about. So error on overflow, saturating types, that kind of thing. We can't do that in Java. And C# source generators should allow us to overcome pretty much any problem that I think we're going to face. And those analyzers and code fixes are all also awesome. We'll talk about those later. So yeah, that's the reason why not using Java for this. But it also had a ton of value, so I love the idea of it. And we're going to bring that to Finn. Okay, next up, we've got embedded C, software testing, and design choices with associated challenges. Thank you very much for hanging out with me, and we'll catch you in the next one.